Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this the lecture number 22 of the course Stochastic Hydrology. In the last lecture we concluded our discussion on time series analysis. Essentially in the last lecture we discussed another case study that of Sakleshpur annual rainfall data, where we considered the time series plot, the correlogram plot, the partial autocorrelation functions and the power spectrum. We formulated candidate ARMA models for this data. For each of the candidate models, we computed the mean square error as well as the likelihood values, and then we chose models corresponding to the maximum likelihood as well as minimum mean square error. The maximum likelihood values will choose a model which can be used for long term synthetic generation of data, whereas we use the minimum mean square error criteria for one time step ahead forecasting, and typically for flow forecasting we use such models. Then we also discussed for the case study the validation tests. Typically the validation tests that we carry out on the residual series are first to make sure that the residual series has a 0 mean, and next we look for any significant periodicities. The residual series should not have any periodicities, and the third test that we carry out is to make sure that the residual series that we get is in fact uncorrelated or it constitutes a white noise. Then we also had a overview of all the case studies that we considered, namely the Bangalore daily data of rainfall, and then the Bangalore monthly data of rainfall, annual data of rainfall. Then we looked up for the case study of Kaveri river flows. We considered the monthly stream flows and distinguished the monthly stream flow correlograms, spectral density etcetera with the daily rainfall correlogram, spectral density and so on. Then we also considered a western river, US river, same monthly stream flow time series we considered, and then we went on to consider the Sakleshpur annual rainfall data. As I mentioned in the last lecture, towards the end of the last lecture, we now proceed to another topic. So, we formally close the discussion on time series analysis. We proceed to another topic. This is called as the Markov chains, and I will give you some introduction about Markov chains, and then we will see in today's class some applications of the Markov chains in hydrologic problems. What do we mean by Markov chains? In fact, in one of our earlier lectures I had introduced a model based on the Markov processes. Now, we will go to the more general Markov chain application. We formally define the Markov chain as follows. A Markov chain is a stochastic process with the property that the value of the process x t at time t depends on its value at time t minus 1 and not on the sequence of other values x t minus 2, x t minus 3 etcetera x 0 that the process passed through in arriving at x t minus 1. In other words, we write this as probability that x t given x t minus 1, x t minus 2 etcetera x 1 and x 0 is equal to probability that x t given x t minus 1. What does this mean? This means that given the entire history of the process from x 0 to the previous time period x t minus 1, the conditional probability x t given the entire history can be equated to probability of x t given just its immediate previous value x t minus 1. In other words, the memory of the process is only restricted to the previous time period. Probability of x t given x t minus 1 determines the state to which the process goes from t minus 1 to t. In other words, all other states in the previous periods that it passed through to arrive at x t minus 1 do not contribute to the state in x t. Only x t minus 1 contributes to the state x t in time period t. Look at the example of, let us say, the monthly stream flows. Let us say we are looking at monthly stream flows, and then we have the stream flow sequence like this. This is the time scale t, and then we have x 0, we are progressing in this time, x 1, x 2, etc., and we have come to x t minus 1, and then we are looking at x t. So, let us say these are monthly stream flows, and you have constituted a time series of monthly stream flows, and then we are at a particular time x t minus 1. We are looking at what is the probability that the process goes into a particular state. I will define what is the state. It takes on a particular value in time period t given the entire history up to this point. Now, this, if we can write it as probability of x t given x t minus 1 etcetera x naught, if this can be written as simply probability that x t given x t minus 1, then this constitutes a Markov chain. And in hydrology, there are a large number of applications of the Markov chains. Specifically, when we are talking about the stream flow sequence, the rainfall during certain time intervals, the reservoir water levels, the groundwater levels, which constitute a time series like this, often we use the assumption of the time series constituting a Markov chain. And we will now see in this lecture how we analyze such Markov chains, such time series, which we will analyze using the assumptions of Markov chain. Now, because the probability of x t depends only on the previous time period, such a chain is called as one step Markov chain. Or a single step Markov chain. You may also have processes where it depends not only on the previous time period t minus 1, but perhaps on 2 time steps previous to the current time period. That is, x t may depend on x t minus 1 as well as on x t minus 2. X t may depend on x t minus 1, x t minus 2 and x t minus 3. Let us say you are looking at hourly rainfall, and then you want to decide on the state of whether the rainfall is 0 or non-zero during a particular hour. Now, this may depend on what has happened during the previous hour, what has happened in the hour previous to that, and so on. So, it may depend not on one time step, but on several time steps. And then we define the n time step Markov chain, n step Markov chain. Now, because we are able to write this expression, probability that x t given x t minus 1 etcetera up to x naught is equal to probability of x t given x t minus 1, we will be dealing with these probabilities now, probability of x t given x t minus 1. And the specific cases that we are dealing with in Markov chain are that the process goes into certain finite number of states, finite or countably infinite number of states. What do I mean by states? For example, we may have the rainy day and non-rainy day as two states, which indicates the weather. So, we may say x t is equal to 0 if it is a non-rainy day, x t is equal to 1 if it is a rainy day. So, x t takes on two states, two possible states. Similarly, if you are looking at reservoir levels, we may say that the level is between 0 to 25%, that is state number 1, 25 to 50%, state number 2, 50 to 75% and so on. Like this, we may discretize the given variable and then define the process to go into one of the states. Similarly, if you are looking at monthly stream flows, we may have a range of stream flows that are possible for the monthly stream flows. Let us say 0 to 400 is the total range of 0 to 400 million cubic meters is the total range of flows that you are considering. In that, we may define certain discrete states into which the monthly stream flow goes. For example, we may say 0 to 100, we call it as state number 1, 100 to 200, we call it as state number 2. So, whenever the monthly stream flow occupies takes a value between 0 to 100, we call it as state number 1 and so on. So, like this, we define the states of the process, states into which the process goes in, and these states can be different during different time periods. Although for most applications, we define the states uniformly all across the time periods. Now, let us understand what we mean by the states and what we mean by the transitions. Let us say this is time period t minus 1 and this is time period t. And now, we define the states as 1, 2, 3, 4 etcetera, m number of states we define. That means, the process in time period t minus 1 can be in any of these m number of states. Like I said, if we are looking at dry day and wet day in terms of whether it is a non-rainy day or a rainy day, then we will have two states. So, the weather can be either in state number 1, which may be dry day, state number 2, which may be a wet day. Or if you are looking at the reservoir storage as a Markov chain, then in time period t minus 1, it may be either in one of these several states, 0 to 25% of the total storage as state number 1, 0 to that is 25% to 50% as class state number 2 and so on. So, we define a priori the states that the process can occupy. So, in time period t minus 1, it can occupy any of these m number of states, exactly one of these m number of states it can occupy. Then in time period t, again it can go into any of these m number of states. Now, starting with a particular state, let us say at t minus 1, let us say we were in state 1, the process was in state 1. It can go to state number 1, state number 2, state number 3 and so on, state number m. The probability that starting with a particular state x t is equal to j given x t is equal to I. Let us say I write like this, where I mean x t is equal to I as the process is in state I in time period t minus 1. This is time period t minus 1. Let me rewrite that. So, this is t minus 1. So, what I am writing is probability that in time period t it goes into a particular class interval given that in the previous time period t minus 1 it was in a class interval I. So, starting with a particular class interval I in time period t minus 1, it can go to either class interval 1, class interval 2, class interval 3 etcetera, to any of these class intervals m, and it has to go to at least one, it has to go into exactly one class interval in next time period t. By class interval I mean the state of the system. This probability that it goes into a particular class interval j, for example 2, given that in the previous time period it was in a particular class interval I, let us say 1, is denoted as p I j t. Let me write that more clearly. This is p I j t, and that is called as the transition probability p I j t, and this is called as the transition probability. So, the transition probability indicates it gives the transition, it gives the probability that starting with the class interval I in time period t minus 1, the process transits into class interval j or the state j in time period t, and we denote this as p I j t. As you can see here, starting with a particular class interval I in t minus 1, it must go into one of them, one of the class intervals 1, 2, 3, 4 etcetera up to m. What does that mean? It means that the probability of going into class interval 1 starting with 1 plus probability of going into class interval 2 starting with 1, probability of going into class interval 3 starting with 1 etcetera. When you add it up, this must sum up to 1, because it has to go into one of these class intervals, one of these states. So, that we write it more formally as summation of, we are looking at j is equal to 1 to m. So, j is equal to 1 to m, where j refers to the time period t and I refers to the time period t minus 1. P I j t must be equal to 1. So, we have two concepts now. One is the transition probabilities. The transition probabilities indicate the probability of the transition from t minus 1 to t. So, what do I mean by transition? That it was in a particular process, a particular state, and then it transits from x t minus 1, it transits to x t, or x t minus 1 is equal to I, it transits to x t is equal to j, and with a probability of p I j t. This is the transition probability. Then, because it has to go into one of the classes, one of the states starting with a given state, the sum of the transition probabilities for any given I must be equal to 1 over all j. So, that is a second concept that we got. So, we write this as sum of p I j t's from j is equal to 1 to m must be equal to 1 for all I. That is, for each of these I, this condition has to be satisfied. And therefore, associated with each of these class intervals I, we have the p I j t's defined from time period t minus 1 to t. Keep relating this with the hydrologic process. We are talking about, let us say, the stream flow during the time period t minus 1 and the stream flow during the time period t, and typically this t can be a month duration. So, we may be talking about the June month flow and the July month flow, and June month flow can take on any state between 1 to let us say 5, 1, 2, 3, 4, 5, and then when I say it has taken a state of 1, we may have a discrete class interval of stream flows associated with that, let us say 0 to 100. Similarly, class interval 2 may have 100 to 200. So, whenever the stream flow is between 0 to 100, I say that it has fallen into class interval 1 or it has taken the value of state 1. And then starting with the particular class interval in t minus 1, it transits into a given class interval j in time period t, and this transition is governed by the probabilities, the transition probabilities p I j t. So, associated with every time period, associated with every class interval I, we have the p I j t's available to us. How we compute is a different story. We will see how we compute this transition probability later on, but now we formulate what is called as the transition probability matrix. So, we write now the transition probability matrix T P M. This is transition probability matrix. And we denote this as capital P, and we write this as, let us say we are talking about t minus 1 here, and the states are 1, 2, 3 etcetera m number of states, and t on this direction we have again 1, 2, 3, 4 etcetera up to m. So, this will be P 1 1, P 1 2, P 1 3 etcetera. That is starting with class interval 1 in time period t minus 1, the probability that it goes into class interval 1 in time period t, in the next time period t, is given by P 1 1. Probability that it goes into class interval 2 in the next time period t, starting with the class interval 1 in time period t minus 1, is P 1 2, and so on. So, this will be P 1 m, that is starting with the class interval 1 in time period t minus 1, it goes into class interval m in time period t, is P 1 m. I am using the class interval and the states analogously. So, whenever I say class interval, I mean it is a state of the system. So, similarly, this will be P 2 1, P 2 2 and so on P 2 m, like this. So, we have P m 1, P m 2 etcetera P m m. So, this is a m by m matrix, where m is the number of states that it can take in time period t minus 1 as well as time period t. So, this we will explain again using more formal notations here. So, this is what we call it as single time step, a single step Markov chain, and then we have a discrete number of states possible in each of the time periods t, t minus 1, t minus 2 and so on. So, we then write the conditional probability. Let us say that our notation is x t is equal to a j, indicates that x t goes into state j, which can be represented by the value a j. Now, when I talk about the applications, this becomes clear. What I mean by that is, let us say state 1 in the case of monthly stream flows. State 1 is defined by the stream flow having any value between 0 and 100, and we may represent that particular class with a particular value of the stream flow. So, we may write it as either x t is equal to j, indicating that x t belongs to the class j, or we may write it as x t is equal to a j, saying that x t takes on a particular value. But essentially we understand that x t has gone into that particular state j. So, this conditional probability now, probability that x t is equal to a j given x t minus 1 is equal to a I. This conditional probability gives the probability that at time t the process will be in state j, given that the process was in state I at time t minus 1. Keep relating this with the physical problem that we just mentioned, that let us say you were in a rainy day. What is the probability that the next day is a non rainy day, or what is the probability that the next day is also a rainy day. So, we are talking about two states here, rainy day is a one state and non rainy day is another state. So, we may say I is equal to 1, I is equal to 2. So, given that we were in a particular state a I, the probability that we go into a particular other state a j, into another particular state a j in the next time period, this is the conditional probability and this is also called as the transition probability. The conditional probability is independent of the states occupied prior to t minus 1, and that is the requirement of the Markov chain. So, we are saying this is single step Markov chain. So, we are saying that probability that x t is equal to a j or x t is equal to j, x t belonging to class j depends only on the state that it occupied in time period t minus 1 and not on any other states that it occupied previous to t minus 1. So, we are interested in, for example, if x t minus 1 is a dry day, we would be interested in the probability that x t is a dry day or a wet day. Typically, this we use in the analysis of rainy days, non rainy days, etc. In the reservoir flows cases, we may use this to develop stochastic optimization techniques, where we consider the inflow data, inflow to the stream flow as a Markov chain, and then discretize the inflow into several number of states, and then identify which state or which class interval the inflow during a particular time period belongs, and then what is the transition probability with which it transits into a given state in the next time period. So, this conditional probability is called as the transition probability or transitional probability. Both of them are used, either we call it as transition probability or the transitional probability, and we denote this as p I j t. So, in our notation, this p I j t indicates that from t minus 1 we are considering the transition to time period t. So, this indicates the transition of the process from a state a I at time t minus 1 to state a j at time period t. Now, we consider a special case where the p I j t is independent of the time. What I mean by that? That once we have the class intervals defined for t minus 1 and t, the transition probability is defined for time period t minus 1 and t. The transition probabilities remain unchanged irrespective of which time intervals you are considering, which two time intervals you are considering. So, if we can approximate p I j t, if we can state that p I j t is equal to p I j t plus tau for all t and tau, that means irrespective of where in the time series you are positioned, the transition probabilities remain the same, then such a Markov chain is said to be homogeneous Markov chain, and we will be dealing with homogeneous Markov chains for the advantage that it provides, the homogeneous Markov chains provide. Let us say now we write the transition probability matrix from time period t minus 1 to time period t. So, like I said, starting with the class interval 1, the probability that it goes into class interval 1 in the next time period is p 1 1. Starting with class interval 1, the probability that it goes into class interval 2 in the next time period is p 1 2, and so on. So, you get p 1 m here, and like this you write starting with class interval m, what is the probability that it goes into class interval 1 PM1, 2 PM2, M PMM. So, this is a m by m matrix and this is the called as the transition probability matrix TPM. Now, because starting with a particular class interval 1, let us say, it has to go into one of these class intervals, the summation of all these probabilities must be equal to 1 as I just stated, and this we write more formally as P I j summation j is equal to 1 to m is equal to 1 for all I. That means, for each of these terms the rows must add up to 1. Now, such matrices where the rows add up to 1 are called as stochastic matrices in the stochastic process theory. The elements in any row of TPM sum to unity. So, this is one important feature. So, all these rows sum to unity. Why does that happen? As I said, starting with a particular state, it has to go into one of the states. So, the probability that it goes into 1 starting with 2 or it goes into 2 or it goes into 3 etcetera, this must be 1. So, it has to go into one of the class intervals and therefore, the rows add up to 1. Now, how do we determine this transition probability matrix? Remember, we are talking in this particular course with data analysis. That means, we have the observed data. From the observed data, we are developing all these analysis techniques. So, we must have the wherewithal or we must have the method by which we can estimate the transition probabilities. So, let us say we are considering the monthly stream flow time series. That means, for June month we have let us say 50 years of data, July month we have 50 years of data, August and so on. So, if we have 50 years of monthly stream flow data and we are talking about T as a month and we write T and T plus 1 side by side, let us say June and July month side by side, and we reckon the state to which the monthly stream flow went in the month T and the state to which it went in month T plus 1, and from the relative frequency approach we estimate the transition probability. So, this is written here as the estimate of the transition probability P I j. I am removing T here because we are assuming that the transition probabilities remain the same across all the time, is equal to N I j. That means, starting with class interval I in time period T, it went into class interval j. The number of times from class interval I in period T, it went into class interval j in period T plus 1 divided by the number of times it went into class interval I itself, which is summation of j is equal to 1 to m. So, this gives you an estimate of the transition probabilities. Let me explain that a bit more, because in hydrology we will be dealing with this particular problem many times. How do we estimate the transition probabilities itself? So, we will also do some case studies later on, but let us examine how we estimate the class interval from the transition probabilities from one time period to another time period. Let us say we are in T is equal to 1 and T is equal to 2. So, this is T is equal to 1 may be June month, T is equal to 2 may be July month. Because you know what is the state number 1 by our definition, let us say that we are talking about monthly stream flows and then say that state 1 is whenever it falls into 0 to 100, I call it as state 1, and state 2 when it falls between 100 and 200 and so on. Like this we would have defined states, let us say we define 10 states for the stream flows. Then on the observed data you will have the June month flows for so many years. Let us say you have 50 years of data. So, you have 50 values for June month, 50 values for July month. Take the first value of June, look at where does it fall. Let us say it fell between in the state number 3. So, we put it as state number 3, and then in the next time period in the next year in June month it fell in class interval 1. In the next year in June month it fell into class interval 3 again and 4 again and so on. Like this, you identify the state into which the process went in the month of June. Similarly, you identify the state in which it went into in the month of July, 2, 4, 6, 3 and so on. Like this, you identify corresponding to the data that you have, you identify the state into which the process went in 2 adjacent time periods t is equal to 1 and t is equal to 2 in this particular case. Now, let us say I am interested in getting P 1 1, that is probability that starting with class interval 1 in June, it went into class interval 1 in July. What do we do? First of all, you collect all those periods in which it went into class interval 1. Let us say out of 50 times, it went into class interval 1 about 30 times in July. So, in July month, in June month, that is here in June month 30 it went into class interval 1 or the state 1. So, it was in state 1 30 number of times out of the total of 50 times. Then we look at every time it has gone into class interval 1, which means out of these 30 times, how many times it went into class interval 1 in July again. So, we pick up those many numbers in the month of July in which it was in class interval 1 starting with class interval 1 in June month. Let us say this was 15, that means 15 number of times out of these 30 times that it went into class interval 1, it went into class interval 1 again in July month. So, what is the probability of going from 1 to 1? It is 15 by 30 or 0.5. So, this is how we calculate the transition probabilities from the data. So, you have the data, you identify for t and t plus 1, you identify the state to which that particular data belonged depending on the definition of the state that you have done, and then look at how many times it went into a particular class interval I, and then starting with this particular class interval I, how many times it went into class interval a given class interval j in the next time period. So, this is how you calculate the transition probabilities. Now, in this particular example, what will happen is that between t is equal to 1 and t is equal to 2, you get a particular transition probability matrix. Then July to August, you will get another transition probability matrix and so on. So, strictly it is not a homogeneous transition probability matrix in this particular case, but this is how we obtain the transition probability matrices from the data. Now, that is what we mean here. So, this is how we estimate the transition probability matrix. Now, we will look at another important concept. At any time step n, we will denote p j n as the probability of being in state j in time step n. So, this is a we are talking about Markov chain. So, t, t plus 1, t plus 2 etcetera, you have a sequence of the process, sequence of the values of the process across time. So, at any time step n, p j n is the probability of being in particular state j at that particular time n. How do we get this? Which means that if we are starting with time period t is equal to 0, we write this as p j 0 is the probability of being in state j in period t is equal to 0. J is again a finite number of classes, j is equal to 1, j is equal to 2 etcetera. So, in time step 0, p j 0 is the probability of being in state j in period t is equal to 0. So, at period t is equal to 0, it can be either in class state 1, state 2, state 3 etcetera, state m. So, this is how it is written p 1 0, which is in time step 0, it is in state 1, that is the probability of being in state 1 in time step 0, probability of being in state 2 in time step 0 and so on, probability of n being in state m in time step 0. So, this is a 1 by m row vector. This is called as the probability vector at time 0. Similarly, at any time step n, I may be either in state 1 with a probability of p 1 n, state 2 with a probability of p 2 n and so on, probability of p m n, I belong to state m, the process belongs to state m. This is a 1 by m row vector, it is called as probability vector at time n. Let us say that we are given p 0, that means we know that at time t is equal to 0, the probability of being in any of the given states, which means p 0 is given. If p 0 is given, I can obtain p 1 as p 0 into p. What is this p? This p is the transition probability. Because I am in a particular class interval p 1, I am sorry, I am in a particular class interval 1 with a probability of p 1. So, the probability of being in class interval 1 in time period 0 is p 1. If you are in class interval 1 in time period 0, the probability that you go into class interval 1 in time period 1 will be p 1 0 into p 1 1, that is the transition probability. So, given any class interval, any state in time period 0, you go to any given state with the associated transition probabilities, and therefore, the probability vector at time 1 can be related to probability vector at time 0 as p 1 is equal to p 0 into p. I will elaborate this with what I mean by that is p 1 is given by p 1 0, p 2 0 etcetera. This is the probability vector at time period 0. So, you are in class interval 1 in time period 0 with a probability of p 1 0 and so on, multiplied by the transition probability matrix p 1 1, p 1 2, p 1 3 etcetera, p 1 m, and this is the transition probability matrix. What does this give when we multiply this? P 1 0 into P 1 1. Look at this term, that is you were in class interval 1 in time period 0 with a probability of P 1 0. Once you are in class interval 1, the probability that you go into class interval 1 in the next time period is P 1 1. So, this gives you the total probability of going to state 1 starting with state 1 in time period 1. Time period 0. Similarly, if you are in class interval 2, you will be in class interval 2 in time period 0 with a probability of p 2, and if you are in class interval 2, you go to class interval 1 with a probability of p 2 1, and therefore, this gives you the probability of going into class interval 1 with starting with a class interval 2 and so on. So, the first term here p 1 0 into p 1 1, p 2 0 into p 2 1 etcetera, p m 0 into p m 1. This term here gives the probability of going to state 1 when you are given p 0. The second term here p 1 0 into p 1 2, p 2 0 into p 2 2 etcetera. Look at these terms, starting with class interval 1 you are going to class interval 2, starting with class interval 2 you are going into class interval 2, starting with class interval m you are going into class interval 2. So, this term gives probability of going to state 2. So, in essence this multiplication gives p 1, that means in time step 1 what is the probability of going to class interval or state 1, probability of going to state 2 etcetera. This is again a row vector. So, we write p 1 as p 1 1, p 2 1, p m 1 etcetera 1 into m. So, we obtained p 1 as p 0 into p. that means the previous time period we knew the P 0 and multiplied it by the transition probability to get P 1. So, we have obtained P 1 now, that means the probability vector at time period 1 is known. We will now use this probability vector to obtain the probability vector for the next time period. So, I will write P 2 as P 1 into P, but what is P 1? P 1 is P 0 into P, and therefore, we write P 2 as P 0 into P square. P is the transition probability matrix. So, given the probability vector at time 0, you can obtain the probability vector at time 2, and in general you can obtain the time probability vector in times n starting with the probability vector P 0 by P n is equal to P 0 into P to the power n, where P is the transition probability matrix, P 0 is the probability vector at time 0 and P n is the probability vector at time n. Now, as the time progresses, you started with a particular initial state, that means P 0, which is the probability of being in a particular state in time period 0, you know that. Then as time progresses, at a far away time from time t is equal to 0, what will happen? The dependence of the process on initial state at time t is equal to 0, this starts weakening. So, it becomes less and less dependent as the time progresses. Suppose we are looking at a far away time in the sequence, and then we are looking at the probability of the process being in a particular state at that far away time. That may become independent, totally independent of the state with which we started. So, the probability of being in a state j after a large number of time steps becomes independent of the initial state of the process, and because of which we will be able to write this as let me write it here. We will be able to write, what did we do for P 1? We wrote it as, we wrote P 1 as P 0 into P transition probability. Similarly, we wrote P 2 as P 1 into transition probability, and therefore, we can write P m plus 1 or let us say n plus 1, because m I am using it for state, is equal to P n into P. That is, we are relating it with the probability vector of the previous time period. Now, as the time progresses, the P n will not be much different from P n plus 1, or P n and P n plus 1 will converge, because they are not dependent on the initial state. When that happens, we can write that as P n plus 1 is equal to P n itself, and therefore, I will write this as P n into P, and both these are equal. So, I can write this as P is equal to P n plus 1 is equal to P n for large n. I will not say n tending to infinity, I will say for large n. That means, as you progress well into the time, a stage will come for homogeneous Markov chains when the transition, when the probability vectors converge, and therefore, we will be in a position to write this as P is equal to P into P, where P is the probabilities when the convergence occurs, and these are called as the steady state probabilities. This is called as steady state probabilities, or we say that the Markov chain has reached a steady state. Now, that is what is explained here. So, the process reaches a steady state at large n, and then we write it as P is equal to P into capital P. Capital P is the transition probability matrix and small p is the steady state probability vectors. So, as the process reaches a steady state, the probability vector remains constant, that is the idea there. So, determination of the steady state probabilities is an important exercise that we do in Markov chains. That means, given a time series, given a process, we should be able to say the probability with which it goes into a particular state at a certain time period when the steady state is reached. So, that is we determine the steady state probabilities using this expression. In fact, with computational power that is available these days, we simply do it with raising the matrices to several powers. So, the transition probability matrix P to the power 2, P to the power 4, P to the power 8, etcetera. So, we are talking about n step transition probability matrices, the transition probability matrix raised to the power n. As n becomes larger and larger, the probability vector converges, and that is what gives you the probability vector. We will see that through an example presently. So, let us try to understand what we discussed so far with a small exercise. Let us say that we have two states, one is a non-rainy day and another is a rainy day. Typically, this is the problem that we come across in modeling the weather. We say that the starting with a non-rainy day, what is the probability that it goes into a non-rainy day, what is the probability that it goes into a rainy day, and so on. So, we define two states here. State 1 is a non-rainy day and state 2 is a rainy day. So, if we are looking at a particular time t and these are the two states, this is non-rainy day and this is a rainy day. Now, starting with a non-rainy day, again here it is non-rainy and rainy. So, starting with a non-rainy day, what is the probability that it goes into a non-rainy day is given by this. So, 0.7 is the probability with which it goes into a non-rainy day if the previous day was a non-rainy day. So, that is and if the previous day was non-rainy day, the next day will be a rainy day with a probability of 0.3. So, this is how we interpret the transition probability matrix. So, we will first obtain the probability that day 1 is non-rainy day given that day 0 is a rainy day. Then we will see probability that day 2 is a rainy day given that day 0 is a non-rainy day. Similarly, probability that day 100 is a rainy day given that day 0 is a non-rainy day. So, these are the probabilities that we will see this. Let us look at the first problem, probability that day 1 is a non-rainy day given that day 0 is a rainy day. What does this transition probability matrix give? It says state 1 which is a non-rainy day. So, in day 0 you were in non-rainy day, 0 is a rainy day. So, here you are non-rainy and rainy. So, day 0 is rainy. So, you are here now. What is the probability that day 1 is a non-rainy day? So, this is non-rainy and this is rainy. So, starting with a rainy day, the probability that you go into a non-rainy day is 0.4. So, that is what we get here. So, probability that day 1 is a non-rainy day given that day 0 is a rainy day. So, no rain and rain, this is no rain and rain. So, you are here, it is a rainy day in 0 and you go into a non-rainy as probability as 0.4. So, directly from the transition probability matrix you obtain this. We will continue this example in the next class, and then we will also see how for this particular example we can determine the steady state probabilities. So, essentially what we have done in today's lecture is that we have introduced the concept of Markov chain and then looked at what is the transition probability and then formulated the transition probability matrix. From the transition probability matrix, we have formulated an expression to obtain the steady state probabilities. We say that the Markov chain has reached a steady state when the probability vectors are no longer dependent on the initial state. So, the probability vectors converge, and by the steady state probabilities we will be able to say that at any given time step n in future, when the Markov chain has achieved a steady state, at any given time step n, the probability that the process will be in a particular state will remain constant. Then we have just seen a simple example by which we interpret the transition probability matrix for a non-rainy and rainy as two states of the system. Given that the state was in non-rainy, what is the probability that it goes into rainy and so on. So, these are the kinds of problems that we will be examining typically in the Markov chains. So, in the next lecture we will continue the discussion on the Markov chain. We will also look at some numerical example through which we estimate the transition probability matrix, and then from the transition probability matrix we will estimate the steady state probabilities, and specifically for the case study of monthly stream flows in a particular location and so on. So, thank you for your attention. We will meet again.